Hey guys, welcome back. This is video 3 for the lesson on section 5.5, which is on a method of integration called substitution. In the first video, we went over some review material and motivating material for the section. In the second video, the method of substitution was introduced and a small number of examples was completed. In this third and final video for section 5.5, what I'm going to do is go through more examples and also look at the method of substitution for definite integrals, so integrals where there's bounds on them. One of the difficulties in using any method of integration is not just deciding which method to use. So for example, initially deciding that substitution is going to be a strategy to attempt, but even after you make that decision, you often have multiple options for what you could use for the substitution. So in this example, it's kind of one of those cases, and the way I'm going to start this is I'm going to rewrite it in a slightly different way. Tan squared of x means tan of x all to the power of 2. Secant squared of x means secant of x all to the power of 2. So we see that we have two components in this expression that are being plugged in to an operation. We have a tan being plugged into something squared, and we have a secant being plugged into something squared. In terms of what this means for a method of substitution, we could let w equal tan of x, or we could let w equal secant of x. And in this slide, what I'm going to do is pick the one that works out well, and then after I'll show you what would have happened if we use the other choice, if we go with the second option. And I can't recall if I made this comment in video 1 or video 2 about substitution, but most mathematicians, when teaching substitution, they use the letter U for the substitution instead of the letter W. And I have like a long-term reason for using the letter W, having to do with a method of integration called integration by parts. And anyway, there's a reason for this. There's a reason I'm using the letter W, and as far as I know, I'm the only weirdo doing this, but I invite you to use this letter instead of the letter U. Anyway, so the choice here is I'm going to let W equal tan of x, and then continue with the substitution. Okay, so we have w squared times secant of x all squared, and then I'm going to leave a box for the dx. Okay, now we have to replace the dx, so dw by dx, derivative of tan of x is secant squared, which is secant of x all squared. Cross multiply and cross divide, and we'll find that dx is dw divided by secant of x all squared. So I'm going to plug that in. dw divided by secant of x all squared. And we have the secant on top, the secant squared on top canceling the secant squared on the bottom. And that is the hallmark of a good substitution. All the components involving x, the old variable, have disappeared. And we only have the new variable. We only have an integral in terms of w. So antiderivative of w squared dw, which is 1 over 3 w to the 3 plus c, using the anti-power rule. And then our last step that we have to do is we need to undo the substitution and replace w by tan of x. And then one additional step, if you wanted to make this look like what the back of the book would have, or what we would have on a, let's say, an online or in-person exam, we'd write this as tan power 3 x plus c, just using that notation. Fairly ambiguous notation. I don't like it, but we're stuck with it. Okay, now in the next slide, what I want to show you is what would have happened if we used the other option, if we let w equal secant. And I think one comment that would be made if this was an in-class lesson is someone would put up their hand and say, well, what about w equals tan of x all squared? Or w is equal to secant of x all squared? Why don't we do those either? And I would invite you to try them. You might actually make some progress towards a solution. You might find a way to solve it using one of those two approaches. But the one I've shown here is the easiest way. It's the most direct way. Okay, so I'm going to, in this one, I'm only going to do one additional option or one additional attempt. So first thing, the same first step as before. Rewrite tan squared as tan of x squared. Rewrite secant squared as secant of x all squared. Okay, and here I'm going to let w equal secant. For the substitution to be complete, we have to take the derivative of w. Derivative of secant of x is secant of x times the tan of x. Rearrange to get dx all by itself. Dx is going to be dw over secant of x times tan of x, which we can write this as dw over the w times the tan of x, because we said w was secant of x. So I'm just going to use the substitution again. Okay, so that's for that part. So we have tan squared. Nothing gets replaced for that. Then we have secant squared. So that's going to be w squared. And then we have the replacement for the dx, which is dw over w tan x. All right, let's see what comes of this. We have the tan in the denominator canceling with one of the tans in the numerator, and we have 1 power of w, oh, should use that. 1 power of w canceling with the w in the denominator, and we're left with w times the tan of x times dw, and this part is the problem. It's still in terms of x. There is a way to proceed from here using some trig identities and throwing caution to the wind, I guess you could say. It's not a good way to proceed. So I would call this a dead end. We have a mixed expression, two variables, w and x, and it's not simple, straightforward to convert this to be just a function of one of those variables. So, dead end. Even though nothing truly is a dead end, you can always recover some way. The effort required to do it in this case is substantial. All right, next one. So I always like rewriting these. Gives you time to think about them. So I have cosine of x, and then the cosine of the sine of x. And we're going to solve this with a substitution. And what we look for in a substitution is a component of the expression that is being plugged into another component of the expression. Here, we have a sine of x being plugged into the cosine function. So that means the best bet, the best thing to try is w is equal to sine of x, the thing that's being plugged in. Okay, to complete the substitution, we'll need to take the derivative. dw by dx is cosine of x, and then we rearrange to get dx. dx is dw divided by cosine of x. Okay, and then our substitution. Cosine of x stays as it is. We didn't replace it. This cosine stays as it is. We just replaced the interior. So sine gets replaced by w, dx gets replaced by dw over cosine of x. And notice that the cosine on top, cosine of x on top, cancels with the cosine of x on the bottom. We can't cancel the cos w on top. With the cos of x on the bottom, they're different. We cancel things that are the same. Okay, and now we have antiderivative of the cosine of w, dw. Now recall what this means. This means d by dw of what equals cosine of w, and the answer is sine of w plus c. So we get sine of w plus c, and then one more step is to undo the substitution. We said w was sine of x, so we have sine of the sine of x plus c as our final answer. And nothing simplifies. There's no cancellation you can do. As a reminder, we could have done this in all previous examples, but we can check by confirming that d by dx of this answer that we got here, d by dx of the sine of x equals our original integrand, cosine of x times the cos of the sine of x. So that's how we would make sure that we got the right answer. And I didn't purposefully, I was about to say I did, but truly I didn't, I'm gonna lie. I didn't involve the plus c here, but I'll include it because, I mean, that's part of our solution. And it won't ever come into a role where it affects this checking process because the derivative of any constant is going to be 0. So it won't show up on the right-hand side. All right, next one. As usual, I'm going to start by just rewriting it. Give myself time to think about the question. And it's not on your table. So this is not one of the ones that you would do by memorization. If the question was, what is the antiderivative of secant squared, the answer is tan of x. If the question says, what is the antiderivative of secant x times tan of x, the answer would be secant of x. But we don't have a trig function that answers the following question, d by dx of what equals tan of x. So we're not doing this one by memory, we have to do it by substitution. But how? Letting w equal tan of x, how is that going to help us? And the answer is it doesn't help us, it makes things worse. So what I'm going to do is a trig identity, or a trig definition, that tan of x is sine of x over cosine of x. And now we have two options. We can let w equal sine of x. This will work. Or we can let w equal cosine of x. This will also work. But the second one will work better. And I'll say homework. Try this on your own. See what happens. It doesn't work out very well. Try w equals sine of x. I recommend against doing this, but just so you can answer the question yourself, why am I letting w equal cosine of x? The answer to the why is do this, do the other one. Okay, so let's build in the substitution. We're leaving the sine at the top alone. We're replacing the bottom, the cosine with w. Now we have to replace the dx with something in terms of w. So we're going to take the derivative of our substitution, dw by dx. Derivative of cos is negative sine of x. Rearrange to get dx. Dx is negative dw over sine of x. We'll plug that in. Negative dw over sine of x. And the substitution worked very nicely. We can cancel the x term on top of the x term on the bottom, leaving us an expression that's only in terms of the new variable. I'm going to take the negative sign and put it out front because constants like -1 can be factored outside of integrals. And we have 1 over w being the function that we're taking the antiderivative of. This is one of our special case formulas. The antiderivative of 1 over w is ln absolute value w plus our constant integration. And then our last necessary step is to undo the substitution. So negative ln of cosine of x plus c. If you look at formula tables, so books or pages that contain antiderivatives as formulas, you'll see that the antiderivative of tan of x is not given by this expression. So what I want to do next is show you where the usual expression comes from. So I'm going to highlight this as a good answer. I'll call it the best answer. And show you the other answer. Equals the ln of absolute value of the cosine of x to the power of -1, using that log property that we can bring a constant up as a power. And then that's ln absolute value of 1 over the cosine of x, which is, right down there, which is 1 over cos is the secant, ln absolute value of the secant of x plus c. So that's the textbook answer. It's not hard to do, you just have to look for it. You have to know to look for it. Okay, next one. This is one of the harder problems, and it is testable. Finding the antiderivative of the secant of x. There's a few things you can try. You can try writing secant as 1 over cos, and then maybe let w equal cosine of x. Problem is that you get a sine of x that won't cancel with anything after you replace the dx by what it is in terms of w. And you can try other things. You can let w equal secant of x from the very beginning and see how far that takes you. There's a variety of different ways that you can approach this problem, and there are, in truth, multiple ways of getting a solution. But those other ways, those alternative ways, require more advanced methods that we're not going to cover in the course. And to use them would take up, like with the way that I write on these slides, it would take up about 3 slides to do one of those other methods. Actually, and there's another one that would only take 1 slide, but it's quite weird compared to what we're about to do. And you might not believe me when you see what we're about to do. What we're about to do is we're going to do, I call it a magic trick. It's one of my favorite things in mathematics. We've done it a few times. I'm going to multiply by 1. Oh, I'm going to use a different color. Multiply by 1. So there we go. Multiply by a fancy form of 1. And what fancy form of 1 are we going to use? Now, where does this come from? So there was, at some point in time, a genius who came up with this particular solution. I am not that genius. Not even close. I would never dream something like this up. But what their form of 1 is that they thought to use is the secant of x plus the tan of x divided by the secant of x plus the tan of x. Why? It works. That's the real answer. It works. And they would have looked at this and knew it worked before they did it. That's the scary part. These people are out there. Okay, let's see how exactly it works. Let's go through the process of solving the problem. So we're multiplying by that fancy form of 1 secant of x plus tan of x divided by secant of x plus tan of x. And I'm going to drop the color red in the next line. Expand out the top. So the top is now secant squared x plus sec x tan x. The bottom is sec x plus tan x. The x is hanging out. All right, and now we're going to do a substitution. So I'm going to flip back to the previous slide and look at what we did in the previous slide. In the previous we said, okay, I'm going to use w's cosine of x because the derivative of cosine is negative sine, and when I rearrange, the sign is going to cancel. Now look at this one here. If I let w equal sec x plus tan x, what's the derivative of secant of x? Sec x tan x, the second term. And what's the derivative of tan of x? Secant squared, the first term on top. So structurally, this is very similar to the previous problem. Let w equal secant of x plus the tan of x. Then dw by dx is sec x tan x plus secant squared. Rearrange, and we get dx is equal to dw divided by sec x tan x. And you know, we can change the order of addition here. I'll put the secant squared of x in front. We don't have to do this, but it's going to make the next step look nicer. Seven plus 3 is the same as 3 plus 7. They're both 10. A plus b is the same as b plus a. Order of addition doesn't matter for what we're doing. All right, so let's see how the substitution fits in, and you can already see it. You can already see what's going to happen. You can already tell this was a good idea. So we thank the random genius. It's kind of what we do in all of mathematics. We copy what was successful until we know enough to do our own creative things. And we cancel. We cancel the sec squared plus sec x tan x on top with the same term on the bottom. And we have antiderivative of 1 over w, which we've already faced. This is just like the last one. We get ln absolute value of w plus c, and then we can undo the substitution. Okay, so that's our answer. It's a classic. I'm going to give you some homework here. I'm going to see who's watching the videos and paying attention by who posts it to the forums. I want you to post this one to the forums. I want to see who can do it. Integral of cosecant of x and I will tell you what the hint is. I'll tell you what the form of 1 is. You'll use 1 equals cosecant of x plus cotan of x divided by cosecant of x plus cotan of x. And see how it goes. Okay, next one. We're looking for the antiderivative of this expression. We have two candidates. We can let w equal x, which never ever will work. It's never helpful. Or we can let w equal ln of x. And that one will work. So ln of x is the element that's being plugged in to something. Okay, so to start our substitution, we have integral of w to the 3 we're going to replace the dx, and what we want to have happen is we want the x in the denominator to cancel with an x in the numerator. So we're really hoping to get that to happen inside this dw by dx term. So dw by dx is 1 over x, and cross multiply, we get x dw is equal to dx, and there we go. We can see it's going to work. So this gives us an x on top to cancel the x on the bottom. So x times dw. The x's cancel. We have integral of w to the 3 dw, which is 1 over 4 w to the 4 plus c, using the anti-power rule. And then we can sub back our substitution to get our answer in terms of x, in terms of the original variable. So 1 over 4 ln of x to the power 4 plus c. Okay, homework also. Post this to the forums if you're up for it. Share the solution with the class. What is the antiderivative of ln of x to the power of n dx all over x? So for any power n, I'll put it that way. For all n values. Give you a hint. One is special. One of the particular values, one of the n values is a special one. The rest are not. Okay, next one. Here we have a clear candidate for the substitution. We have a ln of x being plugged into the cosine function. Wait a second, this is just like the last one. Here we had ln of x being plugged into power 3. Here we have ln of x being plugged into cosine. We have an x in the denominator. The last one had an x in the denominator. You may be able to guess what will happen. There's a similar structure. Okay, so to build our substitution in pieces, we have a cosine of w on top, x on the bottom, and then we're going to replace the dx. I'll leave a box for that. And we know what the goal is. We want to have an x on top to cancel the x on the bottom. And we did this in the last example. We took the derivative of ln of x, we got 1 over x. And then cross multiplied, x times dw is equal to dx. The x's cancel top and bottom. And we have an expression in terms of only one variable, the new variable. The old variable is completely gone. Antiderivative of cosine is sine w plus c, and then we undo the substitution. Sine of ln of x plus c. Okay, there we go. Next one. Few clear choices for what to do. I shouldn't say clear choices. There's a few options that may stand out at you. One of them is we have a 60x squared plus 100 in a bracket. Maybe we let w equal that thing. But maybe or hopefully more tempting to you is the x cubed plus 5x, which is all inside a bracket of the power of 9. I'm going to choose that one. I'm going to let w equal the thing that's being plugged into the power of 9. Let w equal x cubed plus 5x. Okay, we know that ultimately we're going to have to replace the dx, so I'm going to get that work done right away. dw by dx is 3x squared plus 5. Then we cross multiply and cross divide. We get dx equals dw over 3x squared plus 5. Okay, so let's go through the substitution. This is w to the power of 9. Things are not looking good. See this 60x squared plus 100? Well, look what we're replacing for dx. We're putting in dw over 3x squared plus 5. It's not going to cancel. And based on everything that you've learned in the lesson so far, every other example, including the examples that were dead ends, this looks like a dead end. This looks like we failed to solve this using substitution, but we haven't. We have not failed. Let's do some common factoring. So out of that top bracket, what can we factor out? Well, we can factor lots of stuff out, like 10. We take 10 out, we'd have 6x squared plus 100. We can take 20 out and take more. Let's take more. And I'm not taking out necessarily the most that I can. I'm not common factoring. In this case it is, but in some cases it's not. I'm common factoring as much as I need to common factor out to match the expression in the denominator. If possible, in this case it is possible. So I take 20 out, left with 3x squared plus 5. Exactly what I have in the denominator. Now, if that didn't work out properly, then that would mean that substitution was not the method to use. So let's say that 60x squared plus 100, if it was 60x squared plus 80, then when we common factor 20 out, we have 3x squared plus 4, and then those two terms wouldn't cancel. So it would be stuck, kind of. Let's do something different. Don't trouble yourself with what that different thing is right now. You wouldn't get that type of a question. You get this type of a question, maybe. All right, so I took the 20 out front because it's a constant. Now we're going to take the antiderivative of w to the power of 9 using the anti-power rule. We get 1 over 10 w to the 10 plus c. 20 over 10 simplifies to 2 w to the 10 plus c. And then our final step is to replace w by x cubed plus 5x. Okay. We got left. Okay. So it looks like I'm a liar. I'm going to make a fourth video. This is already a long video. I'll continue these two examples in the next video, this example in the next video, and then some more theoretical stuff, followed by a discussion of how does substitution work when the integral has bounds, when you're integrating from a to b. So I'll see you in video 4.